In this lecture, we're going to talk about cardinal arithmetic and the continuum hypothesis. By Cantor's theorem, we know that the cardinality of a power set of a cardinal kappa is always strictly greater than kappa. We also have the definition of a cardinal successor, which we denote by kappa plus. So this means kappa plus is the smallest ordinal that's strictly bigger than kappa. Such a cardinal must exist because we know that there's at least one, and since every cardinal is an ordinal, there must be at least one that's greater than kappa. The question is now, how does kappa plus relate to the cardinality of the power set of kappa? We know by definition, right, since this is the least one greater than kappa, we know that kappa plus is less than or equal to the power set of kappa. The question is a strictly less than possible here? The problem when we're comparing the two is really the way that those two are defined. They're really rather different. So the power set is defined from below using a smaller set by just collecting all the subsets of kappa in a set. That gives us the power set. Whereas kappa plus is defined from above, right, using the cardinals that are bigger than kappa, right, but are unknown to us in a sense. Right? There's a vast universe of them out there. So let us try first to better understand how we can build cardinals from given sets, or how we can not build them. And this takes us to the concept of cardinal operations. Just like with ordinals, we can define arithmetic operations for cardinals. So we have three basic operations how we can join sets together to produce new sets, and we can look at the corresponding operation on the cardinal side. So one thing we could do is to take the disjoint union. So if we have x and y, we can just take a disjoint union of them, and the corresponding cardinal operation would be considered a plus, right? So this would be by definition the sum of the cardinality of x and the cardinality of y. We could also look at the product of two sets, so x times y, and on the cardinal side that would correspond to multiplication. And we can also look at the maps from y to x, written as x to the y, and that would correspond to cardinal exponentiation. So we can use these correspondences actually to define cardinal arithmetic. So for example, if we want to define kappa plus lambda, we can just think of these cardinals here, kappa and lambda, as disjoint sets, and look at their disjoint union, right? And look at their this gives us a set, and then that set has a cardinality, and the cardinality of that set, of the disjoint union of the two, we would define to be the sum of kappa and lambda. Similarly for cardinal multiplication and cardinal exponentiation. So for example, cardinal exponentiation, we would look at the set of all maps from lambda to kappa, right? That's a set that becomes has a cardinality, and therefore it has as its canonical representative a cardinal, and that cardinal we define to be the result of the cardinal exponentiation kappa to the lambda. We have to be careful here not to confuse these arithmetic operations on cardinals with the corresponding with the operation on the corresponding ordinals. So they do not coincide. Right? So for example, let's take omega, right? We have an ordinal addition on ordinals, so omega plus omega, and we've seen that this is not equal to omega, right? However, on the cardinal side, we just defined the addition of two cardinals to be the cardinality of the disjoint union, right? That means the sum of Aleph naught plus Aleph naught, which is the cardinal corresponding to omega, is just the cardinality of the union of two countable sets. The union of two countable sets is again countable, so it has a cardinality Aleph 0. The basic properties of cardinal arithmetic are therefore also different from properties of ordinal arithmetic. So there are plus and times are associative, commutative, and distributive. We also have power laws as stated here. And we also have a monotonicity for exponentiation. You should think a moment about how to prove these identities here. Usually the quickest way is to find suitable injections. Of course, you could also try to find bijections directly, but using the Cantor-Schroeder-Bernstein theorem, it's enough to find injections in each direction. So for example, this identity, so here, that this one cardinality is equal to this one, right? So this set is defined by the set of, so this corresponds to a set of all mappings from C into a product, right? And here, this one would correspond to a product of the set of all mappings from C into A and from C into B. And then you'd have to find an injection, for example, from this, how you turn a mapping from of this kind into a mapping of this kind, and vice versa. Let's do a few examples of cardinal exponentiation. First, we can observe that with our definition of cardinal exponentiation, the cardinality of a power set of kappa is equal to 2 to the kappa. And the way that you prove this is, of course, you identify a subset of kappa with its characteristic function, right? Which is 1 if x is in A and 0 if x is in the complement of A. Right? So this implies then, of course, that using Cantor's theorem, that kappa is always less than 2 to the kappa for every cardinal. Similarly, we can show that the cardinality of the real numbers is equal to the cardinality of 2 to the Aleph naught. Now, a subset of the real numbers, right, will correspond to an infinite binary sequence, right? That we can map to the binary expansion. And this way we can, of course, surject 2 to the Aleph naught onto the, let's say, the open unit interval, which we then, using a suitable function, can biject onto R. And it can actually be modified, this mapping can be modified to become 1-on-1. So you should fill in the steps or the details of this argument. Let's do one more example. So we want to show, we're looking at the set of open subsets of R, and the claim is that the cardinality of this is the cardinality of R, so 2 to the Aleph naught. Think a little bit about how you would prove that. So one direction is pretty straightforward. Namely, we can just inject R into O by mapping a real number to this open interval. On the other hand, every open set is a countable union of intervals with rational endpoints. So that makes it possible to construct a surjection from the power set of Q cross Q, right, onto O, right, a set of open subsets. And we know that, or we can show that, and you're encouraged to verify this, that Q times Q, right, is countable. That now implies that 2 to the Aleph naught, which is the cardinality of the reals, is less than or equal to the cardinality of O because of this injection. On the other hand, we can surject this set onto O. That means O, the cardinality of O is less than or equal to the cardinality of this power set here, which is by definition the cardinality of 2 to the q cross q, and that's equal to, and you can think about how you would justify this here, that's equal to the 2 to the cardinality of q cross q, which is 2 to the aleph naught. It turns out in general that cardinals are very robust under plus and times. So we saw already that aleph naught plus aleph naught is equal to the product aleph naught times aleph naught, which is just aleph naught again, right? Because countable plus countable is the same as a countable times countable is equal to countable. This is actually a more general phenomenon, and that's known as Hessenberg's theorem. Namely, we have for any infinite cardinal, kappa plus kappa is equal to kappa times kappa is equal to kappa. So just using plus and times, it is impossible for us to generate a new cardinality. So for the proof, we will need a well order for kappa times kappa, right? Because that's what we're looking at here. We have a well order for that, right? The product well order, which we use to define ordinal multiplication. But this will not be very helpful for us because as we saw, that increases the order type, usually by quite a bit, whereas we want to study the cardinality, so that doesn't really help us for the cardinal case. And it turns out there is such a well order. It's called the canonical well order of ordinal pairs. The definition of this well ordering is a little bit different from the definition of the product order of ordinals that we looked at before. So here we have pairs of ordinals, alpha, beta, and we say this is less than another pair of ordinals, gamma, delta, if and only if either the maximum of alpha, beta is less than the maximum of gamma, delta, or the maxima agree, and the first component is less than the second component, or the maxima agree, the first components agree, and the second components, so the second component beta here is less than the second component delta. This definition is a little bit more involved than the product of orders, but it has the advantage, it has a few advantages. First of all, you should check that every non-empty X, so pairs of ordinals, has a least element with respect to this order. And then you should verify that for each ordinal alpha, the order on alpha times alpha, so if we look at only pairs gamma delta that are less than alpha, right, the order on alpha times alpha induced by this is the initial segment given by everything that lies below 0, alpha. So that initial segment of this order, right, is just the set of all beta gamma that are less than 0, alpha with respect to this order. Now this well order, this canonical well order, has the really nice property that if alpha is a cardinal, so alpha is an aleph beta, right, the order type of this, right, aleph beta cross aleph beta under this canonical well ordering is actually aleph beta, right? So then this immediately implies Hessenberg's theorem. So to show that, you first define a function gamma, which you let be the order type of the set of gamma delta that are below alpha beta, right? And you verify that gamma is 1 to 1, and it is also increasing with respect to the order, right? And so this maps pairs of ordinals into ordinals, right? And so you verify that this is one-to-one and increasing. We've shown before that for such mappings from ordinals to ordinals, right, that this actually has to be an increasing mapping with the property that alpha is less than equal to gamma alpha comma alpha. Okay. Now that gives us one direction, right? That of course shows us that Aleph beta is less than or equal to the order type of Aleph beta cross Aleph beta. So now it remains to show, and that's the harder direction then, that the order type of Aleph beta cross Aleph beta is at most Aleph beta. And here you proceed by induction, by ordinal induction on beta. And what you do is you assume this fails at some stage, and then you use the inductive hypothesis to derive a contradiction. It follows from Hessenberg's theorem that cardinal addition and multiplication are in fact rather trivial. So, namely that the cardinality of a disjoint union of two sets is equal to the cardinality of the product of the two sets. It's equal to the maximum of the two cardinalities. So as a cardinal version of this statement, it's kappa plus lambda is equal to kappa times lambda. It's just equal to the maximum of kappa and lambda. So that's not hard to derive from Hessenberg's theorem, and you should try that yourself. Furthermore, it is also not possible to reach higher cardinalities, so reach in a more metaphorical sense here, higher cardinalities by taking unions of a fixed cardinality. Namely, the cardinality of a union of a set xi over some index set I, so this would be I and I here, right, is less than or equal to the supremum of the cardinalities of the xi, and of course we have to throw in the cardinality of I here, because we could take a union of a disjoint union of very small sets, but we can take a really big union, so that would make that very large. So that's why we have to throw in the cardinality of I here. This holds provided at least one of the xi is infinite. And you should think of a counterexample that provided this does not hold, right? As a consequence here, we get that, for example, countable unions of countable sets are countable. The idea for the proof of this is as follows. You let kappa be the supremum of all the cardinalities of the xi's. And it's not hard to see that, of course, then every xi injects into kappa. You use now the axiom of choice to select one such injection, right, for each I in I, and that this kind of group of a family of injections you use to define in turn an injection from this set, which you can think of as the disjoint union of the xi's into kappa cross I. So finally we get to the continuum hypothesis. We've seen that cardinal addition and multiplication are rather simple, right? The situation for exponentiation is definitely not. So the continuum hypothesis says that 2 to the Aleph naught is equal to Aleph 1, which is defined to be the cardinal successor of Aleph 0. Right? And we can generalize this actually from cardinals Aleph 0 and Aleph 1 to arbitrary cardinals. So then the generalized continuum hypothesis says that 2 to the kappa is equal to kappa plus for every infinite cardinal kappa. And in the later half of this course, we will return to this, and this will be in an example of the phenomenon called incompleteness, that the axioms of ZF cannot decide this statement either way, so whether it's equal or not equal.